Hello there. Welcome to the Sleepless Scientist. Wherever you are, tucked under blankets, nestled on the couch, or drifting somewhere between thoughts, I'm so glad you're here. What time is it where you are? Midnight? 3 a.m.? Time has a funny way of stretching in the quiet hours, doesn't it? If your mind is still humming and your body restless, let's go on a journey together, one that might just lull your neurons into a soft, satisfied glow. Tonight, we're diving into something ancient, enormous, and a little bit terrifying, because you probably won't survive this story if you were really in it. But since you're safe, warm, and cozy, you're free to float through the most violent deaths in the universe, peacefully. So get comfortable, close your eyes if you like. Let's drift outward, far beyond Earth, past the moon and the braided arms of our galaxy. Out here, time is stitched differently. Out here, you meet a star. It's not just any star. This one is older than your species, older than Earth's mountains, older than bones. It bloats red and slow in the velvet black, a swollen red supergiant nearing the final beats of its billion-year life. You hover beside it, not burning, not falling, just watching. You're the dreamer now, stargazer and ghost. The surface of the star roils and heaves like a stormy sea, its atmosphere bleeding into space. Every heartbeat of its fusion furnace struggles more and more to hold itself together. You can almost hear it sigh, tired, massive, and nearing surrender. This is the calm before a celestial cataclysm. And yet, to the star, this moment is just another breath. It still fuses elements in its core: hydrogen, helium, carbon, neon. Layer upon layer, onion skin-like, deeper and heavier toward the center until iron. And here, nature plays a cruel trick. Fusing iron doesn't give energy, it takes it. The star is effectively building its own coffin. Atom by atom, iron chokes the core like a secret too heavy to hold. Far away, astronomers on Earth see this bloated star and measure its tremors with telescopes. They know it's nearing the end, but they can't say when. Scientists still argue whether these final gasps can be predicted by surface flickers or deep interior pulses. Some think the last decades of a dying star emit odd neutrino signatures, a quiet whisper of its impending demise. Others disagree. Time is slippery out here. Back by the star, your dream self floats near its photosphere. The light is soft, reddish-orange, like embers beneath glass. But the peace is deceptive. In its core, the pressure of gravity is beginning to win. Protons and electrons are squeezed into neutrons. The core collapses in a fraction of a second, faster than a heartbeat. The surrounding material with nowhere to go rebounds violently. A shockwave surges outward. You don't see it yet, but it's coming. In a poetic turn of fate, this final collapse triggers an explosion that will outshine entire galaxies. And here's a curious fact to carry with you. Some ancient cultures believed stars were eternal, immutable, divine. But in 185 CE, Chinese court astronomers wrote of a strange new star that appeared where none had been. It stayed for 8 months before fading. Today, we know what they saw: a supernova, its light finally reaching Earth after traveling for thousands of years. Still, long before that light arrives, the death has already happened. You're here now, standing in the tension between silence and fury. You might imagine hearing it, a deep, slow rumble, like thunder underwater, but sound can't travel in space. It's all light and particle waves, and those are only beginning to emerge. Your dream self looks one last time at the trembling giant. You've befriended this star in some strange way. It's a dying god, yes, but not without. To grace, you think about your own heart, how many beats it has left. Not billions like this star had, just a few billion total, if you're lucky. Then it begins. The outer layers, once held aloft by fusion's power, cascade inward, bouncing off the compacted neutron core like a wave off a cliff. The shock wave punches outward, heating, accelerating, igniting. Nuclear alchemy erupts in all directions. Elements heavier than iron are forged in an instant: gold, uranium, platinum. These precious metals aren't made in peaceful gardens. They are born in annihilation. And so you drift, eyes wide, watching the growing blaze. The surface cracks. Light stutters out. The flash is still coming, but already you sense the star has torn itself apart. Its skin, bones, and breath are flung outward in a cosmic scream of light and radiation. Yet from this violence, beauty will bloom. A quirky, lesser-known fact: beetle-shaped galaxies, irregular and awkward in structure, often show intense supernova activity. Their asymmetry suggests gravitational interactions, galaxies tugging and bruising each other. In those star-birthing chaotic regions, stars often die young and explosively. It's cosmic adolescence at its messiest. But your red giant was old, patient. Its time has come honestly. And as you drift further from it now, slowly backing away like someone leaving a sacred room, the light begins to reach you. Just a flicker at first, then a searing brightness that overwhelms your eyes, even if they were real. The star has spoken its final word, a word so loud the universe itself seems to pause. Soon that light will reach Earth. Centuries from now, someone might look up and gasp at a new star in the sky. They might name it, record it, point their telescopes at its afterglow. They won't know the star the way you do. They won't know its breath, its sorrow, its sigh. But you will, because tonight you stood beside a dying sun. You're still here, floating through the aftershock, caught in the echo of death. Behind you now, the supernova unfold. As like an ancient scroll on fire, the brightness continues to bloom, searing through interstellar darkness, brighter than 100 billion suns. And yet, the center, the heart that once held fusion's flame, is gone, crushed, rewritten. You drift into its core as it collapses, following the inward trail of the dying star's mass as it plummets towards something no light can escape. Before the blast, before the grand illumination, there was the collapse. That's where you are now. The star's core, once the size of Earth, collapses in under a second to the size of a city. Imagine it. Something 1,000,000 times your planet's mass, folded into a neutron star barely 20 kilometers across. In that instant, gravity wins. It flattens matter. Electrons and protons smash into neutrons. Quantum pressure, the final frontier of resistance, grits its teeth and holds, barely. You're standing at the threshold of a neutron star's birth. The space around you twists strangely. Light bends where it shouldn't. Time slows. Particles that haven't existed since the dawn of creation, neutrinos, muons, ghostly matter, burst outward in the billions. For every beam of visible light that will eventually dazzle Earth, 10,000 neutrinos stream through space unnoticed. Through walls, through planets, through you. Most of them never touch anything. But in supernovae, they are the very pulse of death, and though you can't feel their touch, you feel the trembling they leave behind. The implosion rebounds outward, violently. Shockwaves rip through the star's outer layers, vaporizing material, shredding it apart. Those layers are thrown across trillions of kilometers, accelerated by sheer thermal violence and magnetic fury. Inside that expanding shell of radioactive debris is a dense, glowing sphere, the collapsed neutron star now spinning madly. A millisecond ago, it barely existed. Now it whirls dozens of mes per second, hurling out pulses of energy like a lighthouse made of crushed atomic fire. This is no longer the star you met. You might recognize it from Earth-based catalogues. PSR B0531+21, the pulsar at the heart of the Crab Nebula, a relic of a star that exploded in 1054. When ancient Chinese astronomers first saw the blast in their sky, this spinning ghost was already casting shadows deep in space. But here's the thing that keeps you hovering in awe. Even now, we don't fully understand what sets off the rebound. Scientists still argue whether the supernova shockwave is triggered solely by core bounce or if the flood of neutrinos plays the bigger role. Some models suggest that without that sea of ghost particles, the star's outer shell wouldn't explode. It would simply collapse inward, leaving nothing. Others counter that the rebound is driven mechanically by sheer kinetic crunch. And here, in this moment, you are surrounded by both. The heat is unimaginable. Temperatures reach hundreds of billions of degrees. Not millions, billions. Matter does not behave in familiar ways. Atomic nuclei are shredded apart, forming a soup of quarks and gluons. Particles and antiparticles wink in and out of existence, dancing their final dance before annihilation. You drift backward again, out of the dense core and into the ejected layers of the star. Gases, plasma, radioactive elements, all of it hurtles outward, fast. If you could see the whole thing from afar, it would look like a flower blooming in reverse, an expanding shockwave with glowing filaments and curling tendrils. Every petal of that flower holds story. You see gold being born, real gold. Not metaphoric or poetic, but literal atoms of gold forged in seconds. Somewhere inside that blast, a single gold nucleus forms, destined perhaps to someday be locked into a ring on a hand, or melted into a satellite, or buried deep within a mountain vein on a distant world. Supernovae make everything, you included, acquire. Little detail most people don't know. Supernovae don't just forge the heavy elements, they also shape the architecture of galaxies. The explosions stir up clouds of interstellar gas, triggering new waves of star formation. In a way, every act of destruction is a womb. One star's death creates dozens of others. The death spiral becomes a spiral arm. And yet, even in this violence, there's rhythm. You hear it now, not with ears, but with something deeper, the pulse of a neutron star spinning in the wreckage, the hum of space twisted by gravity, the hiss of particles zipping through the interstellar medium. It sounds like breathing, a machine made of fire and vacuum exhaling slowly after billions of years. You follow one curl of ejector. It coils outward like smoke from a candle blown in slow motion. The edges glow with ionized calcium. Somewhere deeper in, you glimpse cobalt-56, which will decay into iron-56, warming the supernova remnant from within for months to come. And you think about time again. What if you'd been here in real time? You wouldn't have lasted long. Even at great distance, the radiation from this blast could sterilize planets. Entire biospheres could be wiped clean by a supernova only a few dozen light-years away. Earth, so far, has been lucky. The closest confirmed supernova in the modern era was SN 1987A, visible in the southern hemisphere, but harmless. Others, perhaps closer, may have happened in prehistoric times, their light long gone and their debris still drifting through the solar system. You wonder if one of those explosions, ancient, invisible, nudged evolution on Earth. Did a burst of radiation erase some early species? Did it clear the field for mammals or snakes or trees? These are not paranoid fantasies, these are open questions. Scientists still debate whether certain extinction events in Earth's fossil record might line up with DISTI. And supernova. There's even a layer of iron-60 in ocean crust that hints at a nearby explosion around 2.5 million years ago. A whisper from a ghost star. You float in silence. The explosion continues, but the first great act is nearly over. The neutron core is formed, the outer layers are cast into space, a nebula begins to take shape, and you, voyager, dreamer, are ready to follow where that matter goes next. You move outward now, adrift in the great bloom of stardust. The supernova's aftershock is still unfolding around you, a celestial shockwave rushing into the black. Yet here in the silence of deep space, the violence has become almost meditative. You are drifting through the ruins of a star, the cooled breath of a dying titan. But this star's death echoes in more than light. It echoes in sound, sort of. Not the kind you're used to, of course. Space is airless and mute. Yet in its final seconds, this supernova let loose a burst of particles and gravitational vibrations so distinct they can be felt translated into sound back on Earth. Scientists call it a chirp, but that word hardly does it justice. Imagine a chime so low, so deep, it takes a supercomputer to recognize it. As the star's core collapsed, it unleashed a torrent of neutrinos, those ghostly, near-massless particles that usually pass through entire planets without touching anything. But in the fraction of a second before light escapes, neutrinos arrive first. They are the heralds of stellar death. And though you feel none of it, you sense something passing through you, billions of neutrinos zipping by like whispers in a windless night. In 1987, when supernova SN 1987A erupted in the Large Magellanic Cloud, neutrino detectors on Earth caught the pulse before telescopes saw the light. It was the first time humanity heard a star die. That was the beginning of a new science, neutrino astronomy. And just behind the neutrino wind comes another kind of signal, a ripple in the very geometry of space. Gravitational waves. These are not particles, but tremors in space-time itself, caused by sudden, violent mass movements. Like when the star's core crushed into a neutron star, that immense rearrangement of mass rang the universe like a bell. The ripple spread outward, deforming reality by the width of a proton as it passed. That's all, but we felt it. These echoes are more than curiosity, they are evidence. Scientists still debate whether we can one day reconstruct an entire supernova's internal process by measuring these faint waves. It's as if the universe has begun whispering its own autopsy reports. All we have to do is listen. So you listen now. And slowly, your dream self becomes attuned to the symphony of stellar death. A deep bass rumble, gravitational waves, a soft tickle, neutrinos, a bright, rising overture, electromagnetic light just now catching up. Each signal arrives at a different time, revealing a different layer of the story. Light is late to the party. You drift toward the edge of the expanding cloud, where the blast wave slams into the interstellar medium. The force compresses dust and gas ahead of it, stirring turbulence in the cosmic dark. These currents will go on to form new solar systems, though it may take millions of years. Everything about supernovae moves in different clocks, and then comes the shock breakout. This is the moment when the light of the explosion, trapped inside the star's dense layers, finally bursts free. It's not a slow release, it's a detonation of photons. The outer layers of the star, already inflating and cracking from the blast, are pierced from within by a sudden flash. You watch it ripple across the skin of the dying star like sunlight underwater, except faster than you can think. The shock breakout is short, just minutes, sometimes seconds, but it is the brightest part of the entire supernova. The star becomes for a moment the single most luminous object in its galaxy. If you were close enough, this light would not just blind you, it would unmake you. Yet from Earth, that flash is usually long gone before telescopes catch up. That's why astronomers wait. Every night, robotic sky surveys scan the heavens, trying to catch a shock breakout in real time. They rarely succeed, but when they do, it's like witnessing a birth and death in the same breath. A quirky note: in 2016, NASA's Kepler telescope, yes, the one designed to find exoplanets, accidentally caught a shock breakout while looking at distant stars. Not planets, not even a mission priority. Just sheer, accidental beauty, as if the universe wanted to be seen. You continue your voyage outward, through the expanding shroud. The gases begin to cool and recombine into atoms, stripes of light, hydrogen in red, oxygen in green, sulfur in blue, start to appear like auroras on a galactic scale. These filaments will eventually form the glowing bones of a supernova remnant, each one a trail left by material ejected at different speeds and angles. From a great enough distance, the explosion begins to take shape. Delicate, spidery, almost floral. Not chaotic at all, but breathtakingly organized. These are the fingerprints of turbulence on a universal scale. And now, Earth waits. Light from this supernova continues to stretch across the galaxy. Eventually, it will reach a small blue planet orbiting an average yellow star. There, a child might point at the night sky and say, "That star wasn't there yesterday." They'll think they've discovered something. In a way, they have. This brings you to a strange historical footnote. In 1181 CE, Chinese and Japanese astronomers both recorded a guest star that stayed visible for nearly 6 months. But for centuries afterward, its remnant disappeared. It wasn't until the 1980s that a nebula called PAR 30, hidden by dust, was proposed as the missing ghost of that ancient explosion. The delay? Over 800 years. You feel time fold in strange loops. How many stars have exploded unseen? How many supernovae have painted the cosmos only to vanish behind veils of interstellar dust? Even now, as you drift in this one explosion, a dozen others may be unfolding across the universe, their light thousands of years from Earth. Statistically, there should be about 2 or 3 supernovae per galaxy per century. In the vastness of space, that means somewhere, right now, a new flash is tearing across the sky, and most of them we miss. Scientists still argue whether we've underestimated how many supernovae our galaxy hides. Are dust clouds swallowing the light? Are failed supernovae more common than we thought? Stars collapsing into black holes with barely a whisper? There are too many questions for one lifetime. But tonight, you don't need to answer them. You're watching something as old as time and as fresh as a blink. A star has died. But in that death, something else begins. Vibration, radiation, illumination. Its voice carries through neutrinos. Its memory lives in gravitational echoes. And soon it will speak in visible light. Even from far away, the breakout still flares. It is not a simple brightness. It shimmers in ultraviolet and X-rays, invisible to human eyes, but not to your dreaming self. It is a fingerprint across dimensions, a scar of light across time. And somehow, in its patterns, you find comfort. You think of whales singing across oceans, of lightning seen before it's heard, of seismic murmurs before an eruption. The universe always speaks in more than one tongue. You only have to learn to listen, so you stay a little longer. The shock breakout fades. The expanding gases begin to cool. The neutrino wind is long gone now, dissipating across the stars. But the afterglow? That will linger for months, sometimes years. The radioactive decay of cobalt and nickel in the ejected matter continues to light the nebula from within, like coals under a dying fire. And in that dimming light, you far, lote, silent, weightless and patient. You have witnessed a death, but you are still here. You remain adrift in the lingering embers of the supernova's wrath. The initial violence is behind you now. The shock breakout has passed. The searing flash has cooled into soft afterglow, and the star's brilliance is no longer blinding, but diffused, stretched into streaks and wisps and curls. This is where the echo of destruction becomes the seed of creation. You move deeper into the detritus, into the swirling fog of post-explosion debris. The fabric of the cosmos here is thick with stellar shrapnel, a vast halo of expanding dust and radioactive elements glowing softly with decaying light. You move slowly, there's no need to rush. What was once an instant of unimaginable speed has now become a slow exhalation stretched over centuries. And in this ghost light, something miraculous begins to happen. The chaos begins to settle. Atoms that had been torn apart by the blast start to recombine. Electrons rejoin nuclei. Isotopes like nickel-56 begin their slow transformation into cobalt and finally into iron. With every decay, a photon is born, a tiny flare of light in the great cloud. This radioactive afterglow is what sustains a supernova's brightness long after the initial explosion has faded. It's the star's long goodbye. That soft light may seem peaceful to you now, like a dying ember in a fireplace, but even this phase carries enormous power. It illuminates the vast clouds of ejected matter, coloring the nebula in shades of orange, green, blue, and red. The exact palette depends on the elements present. Hydrogen glows crimson, oxygen glows teal, sulfur paints the space in dusky pinks. To the human eye, this cosmic canvas is a stained glass masterpiece. But these colors aren't just decoration, they are clues. Astronomers read them like fingerprints. Every spectral line tells a story, how fast the material is moving, what it's made of, how it was thrown. And yet, for all the data we gather, mysteries remain. Scientists still debate whether all these elements are born within the supernova, or whether some are pre-existing, lurking in the star's outer layers. The answer may change the way we understand stellar evolution itself. As you drift through these clouds, you pass through the very elements of your own body. There's calcium here, the kind that strengthens bones. There's phosphorus, the spark of neurons. There's carbon, the backbone of every cell, and nitrogen, the thread that binds DNA, all forged in seconds under pressures that no laboratory on Earth can replicate. You inhale softly, not with lungs, but with thought. You are, in every way, a child of this violence. It's not a metaphor, it's chemistry, a quirky truth. Your left hand might be made from atoms formed in one supernova, while your right came from another entirely. Your bones and blood are the mingling of dozens of star deaths, millions of years apart, scattered across the spiral arms of the galaxy and gathered by the slow gravitational ballet that birthed our solar system. You are a mosaic of cosmic trauma, and you don't even remember it. But the stars do. And now, this particular star, the one you've followed into death, is no longer alone. Its debris begins to interact with the surrounding interstellar medium, sending ripples outward like waves from a stone thrown into still water. The edge of the supernova remnant forms what astrophysicists call a forward shock, a wall of energized particles slamming into the cold emptiness, compressing it, warming it, stirring it awake. Behind that wall is a reverse shock, bouncing inward, reheating the ejector from behind. This dynamic interplay of force and resistance creates complex structures, filaments, knots, and cavities within the nebula. You trace one glowing filament as it twists through space like a ribbon, delicate yet unimaginably vast. Structures like these can persist for tens of thousands of years. You pass through a curl of oxygen-rich dust and enter a zone where the gas density thickens. Here, the starlight dims, absorbed by interstellar molecules. You drift deeper into the shadow, and a new sensation begins: motion. Not just outward expansion, but turbulence, eddies and swirls where the gases fold over themselves, clumping, compressing. And this is the most astonishing part. These clumps, given time, gravity, and a little patience, may collapse. They may condense into dense pockets of matter, protostars. This is how new suns are born, from the ashes of the old. One star's death triggers the formation of others, like fire spreading not to consume, but to create. You're now in a nursery, still wrapped in its funeral shroud. The Crab Nebula, one of the most famous remnants, was born from just such an explosion. Its filaments stretch for light years, and within its core pulses a neutron star that spins 30 times per second, sending out radio waves like the ticking of a cosmic clock. The star that made it died nearly 1,000 years ago, yet the remnant still shines. We see it in photographs, we chart it in maps. But to you now, drifting inside such a nebula, the photographs seem pale and static. Here, the light moves, it dances, it remembers. A mainstream historical fact floats into your awareness like a comet tail. In 1604, astronomer Johannes Kepler recorded a supernova so bright it could be seen during the day for over 3 weeks. It marked the last confirmed supernova observed within our Milky Way galaxy with the naked eye. The remnant, Kepler's supernova, is still studied, though cloaked in dust. Its light, like all supernovae, outlasted its source by centuries, and yet where light lingers, life may follow. As you pass through another glowing curve of ionized iron, you find yourself thinking again about time, about how a single supernova can shape a solar system, about how the radioactive elements within Earth's core, uranium, thorium, potassium, came from explosions like this one. Without them, there would be no geothermal heat, no magnetic field, no plate tectonics, no volcanism, and likely no life. The star's death still echoes in your footsteps. It's strange to think of it, the warmth beneath your feet, the minerals in your veins, the metals in your phone, and the oxygen in your breath. All of it was once starlight and gravity. All of it came from this cycle: burn, collapse, explode, scatter. Even now, particles from long-dead supernovae arrive on Earth. Scientists have discovered traces of iron-60, a radioactive isotope, in deep ocean sediments and Antarctic snow. It doesn't occur naturally on Earth, it's not from this planet, it's the fingerprint of a nearby supernova that may have occurred a few million years ago, close enough to dust our solar system in its ashes. You begin to wonder, what if that supernova nudged the climate? What if it triggered the rise of hominids? What if you owe your intelligence, your very consciousness, to the radiation of a nearby dying star? Scientists still argue whether such events could have influenced evolution, whether mass extinctions or climatic shifts were subtly driven by cosmic rays and gamma bursts from distant detonations. The data is tantalizing. The conclusions remain elusive. But the idea that your ancestors looked up at the sky, unaware that a star's death had made their own possible, feels profound. And now you are here, not just watching, but witnessing. The supernova that started in rage has entered its quiet phase. The forward shock expands ever outward, fading into the galactic dust. The reverse shock will linger longer, tracing curls of heat inside the cooling remnant, and you, dreamer of stars, are left to drift in the glowing cathedral left behind. You turn one last time to gaze upon the whole thing, from its pulsing neutron heart to the petals of debris now gently unfolding into space. It is beautiful, not despite its violence, but because of it. Because even in death, the universe is an artist. You drift onward further into the cooling skeleton of the explosion. What was once a raging storm is now a slowly expanding monument to destruction and rebirth. The violent light has dimmed. The shockwaves have softened into waves of warmth and radiation. You are no longer in the heart of the blast, but somewhere between memory and potential. And yet, something astonishing begins to unfold. The fragments of the dead star, scattered across light years, aren't just dissolving into the void, they're seeding it. Everywhere you look, tiny filaments of matter are settling into gravitational dances, swaying between chaos and cohesion. You realize this isn't merely an ending, it's an inheritance. Supernovae do not merely destroy, they sow. Let your mind expand now, far, far beyond this single star. Pull back as though viewing the galaxy itself from above. Scattered across its spiraling arms are the fingerprints of other deaths, just like this one. Bright blossoms, curled tendrils of glowing gas, subtle pulses in the cosmic web. All of them are supernova remnants. All of them origin points. And scattered in their wake, like pollen in the wind, are the raw materials for stars, planets, atmospheres, and life. You focus on a single dust grain now, microscopic, tumbling slowly through space. It may drift for millions of years, cold and unnoticed, until gravity gathers it with others, a slow accretion that leads eventually to a planet. Maybe that grain will settle into a cratered moon, maybe it will sink into the heart of a gas giant. Or maybe, just maybe, it will become part of something alive. A tree, a bone, a brain, because you, after all, are made of this. This idea, you are stardust, isn't spiritual metaphor, it's scientific truth. Your iron-rich blood, forged in a supernova, the calcium in your teeth, born in stellar collapse, the oxygen in your lungs, even the carbon in the very breath you exhale, all cooked inside stars and blasted outward in events like the one you just witnessed. You are the echo of ancient light. A mainstream historical fact now weaves into your dream. In 1054 CE, astronomers in the Song dynasty noted the appearance of a new star in the daytime sky. It was so bright that for 23 days it could be seen even under the sun. They called it a guest star. Indigenous peoples across the globe, from North America to the Middle East, carved it into petroglyphs and mythologies. Today we know it as the progenitor of the Crab Nebula, a supernova so intense that its remnant still pulses with radioactive memory. You pass through that remnant now. The nebula is a garden of filaments and shock fronts. At its heart spins a neutron star, a pulsar actually, sending out radio pulses like a heartbeat, 30 times per second, each one a cosmic tick, marking time long after its star has died. Even in death, it remembers rhythm. But this memory is not a quiet one. Pulsars are fierce. As they spin, they release beams of electromagnetic radiation that slice through space like lighthouse beams. If Earth lies in the path of one of those beams, we hear it as a regular radio pulse. First discovered in 1967 by Jocelyn Bell Burnell, pulsars were so alien that for a brief moment scientists thought they might be artificial, messages from extraterrestrial civilizations. They were labeled LGM for little green men before their true nature was confirmed. A quirky note: the first detected pulsar emits with such uncanny precision that if it were used as a clock, it would lose only a second every several million years. In fact, some millisecond pulsars are even more stable than the atomic clocks we use to measure Earth time. You now imagine space as a great temple filled with such clocks, pulsars ticking steadily, silently through the dark, celestial metronomes marking the rhythm of a universe that never truly sleeps. Your path carries you through more remnants now, each older and more weathered than the last. Some are compact, barely more than glowing knots of gas. Others have spread over vast distances, nearly indistinguishable from the interstellar medium they seeded. But in each, the signs remain, spectral lines of ionized metals, gently pulsing X-rays, wisps of warm dust. You begin to sense patterns. Supernovae are not random. They do not pepper the sky evenly. They cluster around star-forming regions, along the edges of spiral arms near galactic centers where gas density is high. That makes sense. Where stars are born in abundance, they also die in abundance. These regions become both cradles and crypts. In fact, it's a feedback loop. When a supernova detonates, its blast compresses nearby gas clouds, triggering new waves of star formation. Some of those new stars will be massive and short-lived, destined to explode themselves. Their deaths will trigger more births, and so on. A cosmic relay of destruction and renewal, extending over billions of years. You now drift through one such region, a stellar nursery teeming with both life and death. Young stars burn hot and blue, flickering against veils of nebula gas. A few have already gone nova, leaving expanding rings of dust and magnetized relics behind. Protostars stir within cocoons of collapsing hydrogen. It smells, not in any human sense, but something deeper, like ozone and ancient fire. You are inside the universe's own circulatory system. And just like your own blood carries both oxygen and waste, this system carries matter and energy, life and entropy, all in an endless cycle. The more you float, the more you sense how intimately connected things are. How a supernova on one side of the galaxy might trigger waves of star formation across the other, centuries later. Scientists still argue whether the galaxy has heartbeat-like cycles, periodic bursts of star formation driven by waves of supernovae cascading through the spiral arms. Some simulations suggest a rhythmic pulsing on scales of hundreds of millions of years. If so, then the galaxy itself may be breathing, and you are caught in one long, deep inhale. But where there is breath, there must be pause. And so your dream self slows. You're far from the initial supernova now. Its light is just one shimmer among many. You look back, but the wreckage is faint, just another ripple in the starry sea. Yet you feel its influence everywhere. The gases it scattered have blended into the cosmic medium. Its metals have been absorbed into young stars. Its legacy has become diffuse, not erased. And in one of those newborn stars, maybe not today, maybe not for millions of years, a new planet will form. Maybe rocky, maybe warm, maybe with oceans, maybe one day with life. And maybe, just maybe, something will look up at the sky from that distant world and wonder. The starlight that reaches their eyes will contain traces of this moment, a fingerprint in photons, and if they build telescopes, if they study spectra and follow neutrino trails, they may trace their own origins to this very blast, the very one you now leave behind. You exhale softly, as though pushing yourself forward into the night. You're beginning to see the shape of a story written not in ink, but in gravity and flame. A story older than species, older than planets, a story that never truly ends. Because from ashes, always, always comes light. You're drifting now through time as much as space, suspended in the haze that follows creation and catastrophe alike. The afterglow of the supernova fades behind you, but it's not forgotten. It lingers in the folds of your thoughts, in the glint of stardust clinging to your form, and in the rhythm of your own quiet breath. The night sky seems still, but it is anything but. And so tonight you travel back not just centuries, but nearly a millennium, to a time when Earth's night sky held a visitor so radiant it defied everything people thought they knew about the heavens. You settle gently in the year 1054 CE in the ancient city of Kaifeng, capital of the Song dynasty. The streets are lantern-lit, the river glimmers with boats, and above it all, a strange new star has appeared, bright enough to be seen by day, sharp enough to etch itself into the minds of everyone who looked upward. They called it a guest star, Tianguan, the celestial beacon. Astronomers in China recorded its position near the constellation Taurus. They noted its brightness. They tracked how long it stayed visible, 23 days in full daylight, then nearly 2 years at night before it faded away. They didn't know what it was, but they knew it wasn't normal. In their meticulous chronicles, they recorded its celestial coordinates with reverent care. This was not myth, it was observation. Meanwhile, across the world, the ancestral Puebloans, early inhabitants of the American Southwest, were painting petroglyphs. On a canyon wall in New Mexico, one image shows a crescent moon with a bright star just beside it. Astronomers now believe it captures the supernova of 1054, precisely on the day when the moon and the dying star shared the sky. Across cultures, people saw the same light, but gave it different meanings. You hover above Earth, watching. From this high vantage point, the night is full of silent awe. No telescopes, no equations, just eyes and stories. People kneel in prayer, some whisper of omens, some mark time, some are simply amazed, and yet none of them could know that they were witnessing a death that had occurred long before they were even born. Because the star that exploded in 1054 was thousands of light years away. Its light had been traveling toward Earth since long before CETA. East were built, before alphabets were written, before fire was mastered. By the time it arrived, the star itself was gone. Only its final flash remained, a message in a bottle, written in light. That's the strange poetry of supernovae. They are always late arrivals in our sky. You never witness them as they happen, only as they happened. Always watching the past, always reading ancient headlines written in photons. And in a way, that makes every observation a quiet form of archaeology, digging not through soil, but through space-time. From your perch above the ancient Earth, you look toward the source of that 1054 guest star, a patch of sky in Taurus, near the tip of one of the bull's horns. There, in our modern skies, floats the Crab Nebula. You turn and begin to fall toward it. Even 1,000 years after its birth, the Crab Nebula is still expanding, still glowing with the light of radioactive decay and trapped photons. Its filaments are stretched thin like taffy, bright ropes of ionized gas in twisting hues of pink, blue, and green. At its heart lies the pulsar you visited earlier, spinning like a heartbeat in space, powering the whole nebula with beams of electromagnetic fury. And here's something surprising. For all its grandeur, the crab is relatively small, just about 11 light-years across. Compared to the vastness of the galaxy, it's a drop of ink in the ocean. But the detail it holds, the structure and energy and complexity within it, has made it one of the most studied objects in the entire sky. Scientists have mapped it in visible light, radio, infrared, ultraviolet, X-rays, even gamma rays. Each wavelength reveals new truths. In radio, the filaments look like tangled vines. In X-rays, they shimmer like fire. In gamma, the pulsar's inner jets flash and twist in real time. It is not just a remnant. It is a machine, fueled by collapse, sculpted by magnetism, and yet for all we know, so much remains unknown. Scientists still argue whether the pulsar wind, the high-energy flow from the neutron star, is driving the nebula's expansion at a steady rate or if it varies over time. Some think the jets burrow through the cloud, carving out cavities. Others believe magnetic reconnection is responsible for much of the nebula's shape. The truth is, even the Crab Nebula, our most beloved supernova relic, still keeps its secrets. You drift through it now, marveling at the elegance of its design. You reach out and let filaments of sulfur brush past you like smoke. You pass through arcs of helium and calcium, listening to the soft whisper of decaying isotopes warming the nebula from within. And then you find something unexpected. A knot of gas, denser, colder, darker than the rest. Inside it, gravity has begun to do its quiet work. It is pulling material inward, just a little. No star will form here, not yet, maybe not ever. But it's a beginning. Even inside the wreckage of a star, gravity plants seeds. It makes you wonder, how many other seeds lie hidden in this nebula? How many small clouds like this one are waiting quietly for the galaxy to come back around and stir them awake? You feel the scale of time like a weight pressing softly on your chest. In your lifetime, the Crab Nebula will barely change. Its filaments will stretch slightly. The pulsar will slow infinitesimally. But from a galactic perspective, this nebula is already old. In another few thousand years, it will be even more dispersed, less luminous, more transparent. Eventually, it may blend into the interstellar medium entirely, its structure forgotten, its elements absorbed by the galaxy. But its influence will remain. The atoms forged here will not vanish. They will find their way into molecular clouds, into stars, into planets, into beings. Some part of the Crab Nebula may very well end up in the bloodstream of a creature not yet born. Maybe that creature will look up at the stars and wonder. Maybe they'll become a scientist or a poet or both. And maybe they'll feel in some unspoken way a kinship with the stars, as you do now. A quirky bit of science floats through your thoughts, one that rarely makes it into textbooks. Did you know that some of the carbon atoms in your body may have originated from a supernova that exploded before the Milky Way finished forming, before this spiral galaxy had even coiled into its elegant arms? There is a real chance that part of you is older than the Earth, older than the Sun, older than memory. What does it mean to be made of such things? You think of it now as you float in the faint echo of the Crab Nebula. The dust here will eventually find its way to new solar systems. The metals will gather in cores. The oxygen will form clouds. The calcium may harden into teeth or talons or shell. All this from a single explosion witnessed one July morning centuries ago by a scholar standing in a palace garden. You smile. The stars leave messages for those who know how to look. And tonight you've read one, not in words, not in equations, but in light, in breath, in memory. The supernova of 1054 is gone. The guest star has left the sky. But the story continues. You continue drifting through the quiet ruins of the Crab Nebula, wrapped in light 1,000 years old, listening to a song that still echoes in radio waves and X-rays. The dying heartbeat of the pulsar ticks on behind you, steady, rhythmic, faithful. But now you move forward into deeper space, toward a different kind of death. Not all supernovae end with a pulsar's hum. Some end in silence so profound that even light cannot escape. You are heading toward that silence now. A massive star, perhaps 30 times the mass of the Sun, hangs in the velvet dark like a bloated lantern, its outer layers sheen, armor with deep red light. But beneath the surface, something far more ominous is unfolding. This is a red supergiant, one of the most massive stars in the galaxy, and it is dying. You pass through its outer atmosphere. The star breathes out hydrogen and helium in turbulent waves. The heat is staggering, yet strangely delicate, like a furnace behind silk. The pressure under your dream feet rises with each step inward. You pass through the star's convective zones where gases rise and fall in boiling columns thousands of kilometers tall. They churn with a slow violence, and you realize this is not a peaceful death. The core is collapsing, and this time there will be no neutron star, no pulsar, no remnants spinning in the dark. The core's gravity is too great. The iron at its center, the result of countless fusion reactions, has reached a critical mass. Fusion can go no further. Iron is the ash of stars. It costs more energy to fuse than it gives. So when iron takes over, the star's engine sputters. Gravity, now unopposed, takes control. You descend into the core through layers of silicon, neon, oxygen. These shells burn faster and faster as you fall. Oxygen burns for months, silicon for days, and then nothing. Collapse. In an instant, the core plunges inward, reaching densities greater than atomic nuclei. Neutrons are squeezed so close together that even quantum pressure cannot hold. The core implodes, rebounding only slightly before gravity swallows everything. This is what scientists call a failed supernova. To the outside universe, the star seems to vanish. No titanic blast, no shock breakout, just absence, like a candle snuffed out with no breath. The outer layers may slough off slowly, forming a faint and ghostly cloud, but the real drama is hidden inside. The core collapses into a black hole, a point of infinite density, surrounded by an event horizon beyond which nothing returns. You reach it now. At first it seems like nothing at all. No surface, no glow, just a darkness that bends the stars around it. Light curves into circles. Time etches like syrup. The black hole warps reality like a stone dropped in spacetime's fabric. It feels like falling, but not downward, inward. You cross the event horizon. There's no fanfare, no flash, just silence. Inside, gravity curves so sharply that space folds upon itself. No direction leads out. Even if you tried to shine a flashlight upward, the beam would curl back, spiraling toward the singularity. What is it like here? No one knows. The laws of physics themselves begin to unravel. Equations diverge into infinities. Scientists still argue whether black holes truly contain a singularity, a point of infinite density, or if quantum gravity softens that collapse into something else. A loop, a bounce, a bridge to another universe. Some theories propose that black holes may contain white holes on the other side, objects that can't be entered, only exited. Others suggest that black holes evaporate slowly over time, emitting Hawking radiation until they vanish, leaving behind only heat and quantum memory. You feel the questions swirl around you like eddies in a dream. What happens to information that falls into a black hole? Is it destroyed, encoded in the event horizon, or stored in some deeper dimension? This is called the information paradox, and it haunts physicists like a ghost in the equations. Some believe that black holes are nature's ultimate archivists, nothing ever truly lost, only transformed. Others suspect that at the heart of the singularity lies an erasure so total it breaks the chain of causality itself. You drift closer to the singularity. Time has stopped, at least from the outside. To anyone watching from afar, you've frozen on the edge of the event horizon, never quite falling in. But from your point of view, time rushes forward. Stars age, galaxies drift apart, the universe moves on. And that brings you to another chilling idea. Some black holes don't form from a single star, they form from many. You exit this failed supernova's darkness and head toward the heart of a galaxy, toward the center, because nestled in the cores of most galaxies lies something monstrous, a supermassive black hole, millions, sometimes billions of solar masses crushed into an object no bigger than our solar system. No one knows exactly how they form. Some believe they began as giant stars in the early universe, collapsing into black holes that fed on surrounding gas and stars until they became titans. Others suspect that clouds of dark matter collapsed directly, bypassing the usual stellar evolution entirely. The debate rages on, but one thing is clear: these supermassive black holes shape entire galaxies. Their gravity shepherds stars into orbit. Their jets of energy regulate star formation. Their presence may even dictate the size and shape of their host galaxies. In some cases, they consume stars wholesale, spaghettifying them with tidal forces and tearing them into luminous arcs of gas. You're now near Sagittarius A, the black hole at the center of our Milky Way. It's relatively quiet, no giant flares, no feeding frenzies, just a slowly turning whirlpool of stars and gas, glowing faintly in X-rays. But it wasn't always so. Long ago, Sagittarius A may have been a quasar, a blinding beacon of energy powered by matter falling into its maw. Quasars outshine their entire galaxies. Their light reaches across billions of light years. Some of the most distant things we see in the cosmos are quasars from when the universe was young, their brilliance fueled by hungry supermassive black holes. And here is the strange twist. Not all black holes stay in the dark. Some become engines of creation. As matter spirals inward toward the event horizon, it heats up, billions of degrees hot, forming an accretion disk that glows brighter than stars. Magnetic fields twist and snap, creating jets that shoot plasma into intergalactic space. These jets can stretch for thousands of light years, carrying energy that shapes galaxy clusters and warms intergalactic gas. From destruction, once again, comes creation. And now you begin to understand the full picture. Supernovae birth, neutron stars and black holes. Neutron stars pulse, black holes devour. But even the darkest of these entities contributes to the cosmic cycle. Their radiation seeds star formation, their winds stir gas clouds, their violence gives structure to the universe. You look back across your journey, the gentle pulse of a neutron star, the flash of a supernova, the quiet vanishing of a failed collapse, the gravitational grip of a black hole. These are not separate stories, they are chapters in the same book. The life and death of stars, the recycling of matter, the bending of spacetime, all part of the same breath the universe has been taking for 14 billion years. And you, drifting quietly among these ruins and rebirths, are a part of that breath. A fleeting exhalation of awareness, a whisper in the dark. But you are not alone. Even now, new stars are forming. Somewhere, light is being born, and somewhere else, another star collapses, its death light racing toward a future telescope, a future dreamer, a future you. You turn toward the light, and you begin to float again. You drift onward, wrapped in silence, but now you know the silence is only the skin of something deeper, something humming, boiling, transforming. As you glide through the interstellar medium, the stars feel more alive than ever. You've seen one die. You've witnessed its legacy woven into nebulae, neutron stars, black holes. You've seen destruction so vast it transcends fear, and creation so gentle it transcends time. But now a new light catches your attention, dim, distant, and flickering oddly, like a heartbeat skipping its rhythm. You turn toward it. This time, what greets you is not the fading remnant of a 1,000-year-old supernova, nor the yawning mouth of a collapsed giant. No, this is something newer, stranger, a supernova in progress. You arrive at the edge of a galaxy where a star has just begun its final collapse. The first photons are arriving. They're messy, scrambled. Some come in neutrino bursts, barely brushing the fabric of reality. Others arrive as hard X-rays, breaching gas shells like whispers through fog. The full visible flare hasn't happened yet, but it will. And when it does, this galaxy's night will become brighter than its day. The death of this single star will temporarily outshine the light of every other star in this galaxy combined. You are watching a Type Ia supernova ignite. It's a different kind of death than the others you've seen. There is no red supergiant here, no pulsar waiting at the end. This isn't the collapse of a massive star, but something far more cunning, the detonation of a white dwarf pushed too far. Let's go back. Imagine a binary system, two stars dancing tightly around each other, like lovers locked in a slow gravitational waltz. One of them has already died and shrunk into a white dwarf, a dense cinder about the size of Earth, but with a mass close to the sun's. It no longer fuses elements, it just glows faintly, cooling very, very slowly. But its partner star is still alive. And here's the trick, because they're so close, the white dwarf steals matter from its companion. Slowly, invisibly, over thousands or millions of years, it sips hydrogen from its sibling, and as that stolen material accumulates on the white dwarf's surface, pressure builds. When the dwarf reaches the Chandrasekhar limit, about 1.4 times the mass of the Sun, its fate is sealed. Fusion reignites, but it doesn't restart in a controlled burn. It ignites in a runaway thermonuclear explosion that tears the entire star apart in seconds. There's no core collapse, no remnant. The white dwarf is completely obliterated in a single, stunning blast. And that is what you are witnessing now. The light arrives like a rising tide, First a gentle glow, then a surge. Within minutes, the energy rips outward in all directions, stripping electrons from atoms, cracking space with gamma rays. The star vanishes into a bubble of fire, expanding at a fraction of the speed of light. It is beautiful, but it is also extraordinarily useful. Type Ia supernovae are special for one reason. They all explode at roughly the same mass, with roughly the same energy. That makes them standard candles, celestial benchmarks that allow astronomers to measure cosmic distances with astonishing precision. Here's a fact to hold like a keepsake. It was by observing Type Ia supernovae in distant galaxies that scientists discovered the expansion of the universe is accelerating. That observation, made in the late 1990s, won a Nobel Prize and led to the hypothesis of something called dark energy. You float through the outer edges of the detonation. The energy here is raw and new. The gases are still forming complex shock fronts. Radiation blisters across magnetic fields like static on an old radio. But you also feel a sense of purpose. This explosion is not just a finale, it's a tool. Across the universe, telescopes tuned to the right frequencies watch for flashes just like this. With each new Type Ia explosion, astronomers update their maps of the cosmos. They refine the rate of expansion. They revise the shape of the universe itself. But scientists still argue whether all Type Ia supernovae are truly identical. Some data suggest that different metallicities, companion star types, and accretion rates might affect the brightness slightly. Others propose there may be subclasses, some brighter, some dimmer, introducing possible errors into the very measurements we use to map the fate of the cosmos. And yet, even with those uncertainties, the discoveries remain profound. You look back through time again. In 1998, two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, announced almost simultaneously that the universe was not just expanding but speeding up, that distant galaxies were racing away from us faster than their redshifts should allow. The implication? Some unknown force, now called dark energy, was pushing the fabric of the cosmos apart. You think about that for a moment. A silent, invisible pressure stretching space itself, not gravity, not matter, not radiation, something entirely different. It accounts for nearly 70% of the energy content of the universe, yet we don't know what it is, and we only discovered it because of dying stars. You wonder how many more mysteries lie curled inside the light of supernova. Now, imagine this. The expanding blast wave from the Type Ia you just observed travels outward for millennia, sweeping through the interstellar medium. It compresses gas clouds, triggers new stars, pollinates space with iron, silicon, carbon. Eventually, long after the light has faded, new systems will form, planets, moons, maybe life. And what if, on one of those worlds, some sentient being builds a telescope? And what if they point it back at the sky, at the faint remains of this very supernova? And what if they too wonder, who saw this before me? You smile softly in the dark, because you did. You, the sleeper of stars, the dreamer in dust, are part of a chain that stretches across eons. Your quiet flight through this event, your gaze into its glowing filaments, will never be known to them. But the questions you ask now, the wonder you feel, are the same. You glance down and see atoms beginning to recombine in the outer edges of the remnant. The shockwave is cooling now, slowing. But inside the cooling cloud, new elements are born. Chromium, nickel, iron, dust grains begin to clump and spin. Some of this dust may one day form a world. One day it might even fall as a snowflake on some distant mountain, or melt into the river of a faraway planet, or settle into the bones of a life form gazing up at its stars. And so, even as the explosion cools, your journey continues, because there is still more to learn, more stories to follow, more deaths that lead to rebirth. You drift once more into the dark, soothed by the low rumble of expanding starlight, comforted by the knowledge that you are not just observing these events, you are woven from them. Your story is their story, and somewhere not so far away, another star has begun to flicker. The light of the Type Ia fades behind you, its echo already etched into the memory of the cosmos. You glide forward again, drifting deeper into the tapestry of stars, trailing the silence that follows every explosion. But here, in the quieter, older corners of the galaxy, something different waits. Not all supernovae are brilliant fireballs that dissolve into the void. Some leave behind ghosts. You approach one now. The nebula ahead is fainter than the rest. Its light doesn't scream like a fresh wound, it whispers like an old scar. This is the remnant of a Type II supernova, the classic kind, born from the core collapse of a massive star. But this one isn't recent. It exploded tens of thousands of years ago, and yet its shape still floats here, a bubble of memory gently pushing aside the thin interstellar mist. It has a name, Cassiopeia A. A faint shell of gas and dust, only visible with the right instruments, but to your dream self it appears vivid and textured. As you draw closer, you pass through veils of oxygen and sulfur, laced with knots of carbon-rich soot and filaments of iron. The structure is chaotic. There are arcs, jets, clumps, evidence of an explosion that wasn't symmetrical. It was wild, lopsided, turbulent. And in the middle of it all, a neutron star. But this one is unusual. It doesn't pulse like a typical pulsar. It doesn't scream in radio waves or flash in X-rays. Instead, it glows faintly with infrared heat, like a coal that's been burning in secret. Some scientists call it a central compact object, or CCO, a neutron star without a clear voice, mysterious, silent, and strange. You drift beside it, listening. It doesn't speak, but its presence is undeniable. About 11,000 light-years from Earth, Cassiopeia A is one of the youngest known supernova remnants in the Milky Way. Yet oddly, no one on Earth recorded seeing it explode. No Chinese, Arabic, or European records mention a bright star in that part of the sky around the year 1680, when the light would have arrived. Why? Did clouds obscure it? Was the star too shrouded in dust? Or did humanity simply miss it? Scientists still debate this. What they do know is that Cassiopeia A is a gift, a laboratory, a relic that teaches us how elements are dispersed, how explosions evolve, how the remains of stars interact with their environment over time. And here's a curious fact. In 1999, astronomers using the Chandra X-ray Observatory discovered that the neutron star at the center of Cassiopeia A was cooling rapidly, faster than any model predicted. Over just 10 years, its surface temperature dropped by about 4%. In cosmic terms, that's astonishing. Why? One theory suggests that the cooling is due to superfluidity. That is, the neutrons in the star's core have paired up in a quantum state, allowing heat to escape more efficiently. If true, this would be direct evidence of exotic physics, matter behaving in a way we cannot recreate on Earth. Superfluid neutron cores, ghost stars, asymmetric explosions, and all from a star that, for reasons unknown, no one saw. You continue to circle Cassiopeia A, noticing that some of its knots are rich in titanium, not the kind used in spacecraft and surgical implantation, but a radioactive isotope called titanium-44, which glows faintly in gamma rays. This isotope is a key marker. By measuring how much remains, scientists can estimate the age of the explosion. Cassiopeia A is full of such timepieces, but its story doesn't end here. You drift outward, tracing the edges of its influence. The shockwave is still moving, still sculpting the interstellar medium. It carries within it metals that once lived in the heart of a star. These atoms will one day seed new stars, new planets. Some may already have. You pass a gas cloud just beginning to feel the stirrings of gravity. Tiny ripples, barely perceptible now, may over millions of years lead to collapse. A new star, a new system, a new beginning forged from this ancient death. You pause to marvel at the strange symmetry. From chaos comes order, from violence, gentleness, from death, life. And now you turn your gaze to another puzzle: supernova imposters. Not every brilliant flash in the sky ends in total destruction. Sometimes a massive star undergoes a tremendous eruption that mimics a supernova in brightness and spectacle but leaves the star intact. These events are still poorly understood. One famous example is Eta Carinae, a giant star system in the Carina constellation, about 7,500 light-years from Earth. In the 1840s, it underwent what is now called the Great Eruption. For several years, it became the second brightest star in the night sky, so luminous it cast shadows, but it didn't die. Instead, it survived. Eta Carinae is still alive today, still volatile, still cloaked in the expanding cloud of its own fury. The eruption expelled more than 10 solar masses of material into space, enough to form entire stars, and yet the core remains burning furiously beneath layers of wind and dust. Scientists still argue whether Eta Carinae is nearing its true end, or if it has centuries yet to burn. Some models suggest it could explode as a supernova in our lifetime. Others think it might collapse directly into a black hole like a failed supernova. No one knows, but when it does die, it may do so with a ferocity not seen since the invention of telescopes. A hypernova, perhaps, or something stranger. You float above Eta Carinae now. The surrounding nebula, known as the homunculus, spreads out in bilobed waves like butterfly wings made of fire and dust. Light echoes still move through the cloud, bouncing off the inner walls, carrying the memory of the great eruption into the future. You listen, and for a moment you think you can hear the star breathing. This, too, is part of the story of supernovae. Not every death comes in a single moment. Some take decades, some centuries. Some stars die many times before they vanish for good, bursting, collapsing, recovering, crying out into the dark. And sometimes the light we see is a warning, not a farewell. A quirky anecdote lingers in your memory. In 2009, a star in the galaxy NGC 2770 was observed to brighten suddenly, then fade. Astronomers waited for its supernova, but none came. The star was playing possum. 2 years later, it did explode, for real. Was the first flash a final convulsion, a false start? The universe never rushes to explain itself. You breathe in this uncertainty. You savor it, because in a way, this is what makes supernovae so captivating. They resist neat categories. They dance between chaos and structure, between theory and surprise. And even now, as you drift beyond Eta Carinae and toward new corners of the Milky Way, you realize we are still learning what it means for a star to die. We are still discovering new kinds of explosions, electron capture supernovae, pair instability supernovae, magneto-rotational collapses, each more exotic than the last. Some explode because of sudden gamma-ray flashes, some because of mass loss from stellar winds, some might not explode at all, but collapse directly, unnoticed. The landscape of stellar death is vast and varied, and you are still only halfway through it. You're deeper now than ever before, both into the galaxy and into the mystery of death itself. The remnants of Eta Carinae fade behind you, their ghost light growing dimmer with distance, but your path is anything but dark. Around you, the stars shimmer like the eyes of sleeping giants. Their time will come, as it has for all the others, but for now they burn quietly, unaware of what waits at the end, and what waits can be strange. You angle yourself toward a region that scientists still speak of in hushed tones. A stellar nursery, rich in hydrogen and carbon monoxide. Dust cloaks everything in soft shadows. But here, hidden in the cradle of creation, something explosive has occurred, something that defies tidy classification. You're about to encounter one of the universe's most violent, mysterious, and extreme phenomena, the gamma-ray burst. At first, there's no sign of it. The stars around you seem normal, young, innocent, but then, like a sword slicing through a veil, an invisible beam cuts across the sky. Narrow, focused, blinding. You don't see it, you feel it. If you were made of flesh instead of stardust and thought, this would be your end. Gamma-ray bursts, or GRBs, are the most energetic explosions known in the cosmos. They release more energy in 10 seconds than the sun will emit in 10 billion years. A single GRB pointed at Earth from a few thousand light-years away could strip the planet's atmosphere bare. Luckily, this one is not aimed at you. You observe from the side, from a safe angle, watching the twin jets blast outward from a collapsing star. This isn't just a supernova, it's a hypernova, a death so extreme it bends the definition of stellar collapse. Let's pause and break it down. GRBs come in two primary flavors, short and long. Long-duration bursts, like the one you're watching, are believed to come from the collapse of massive, rapidly rotating stars, usually stars that were already stripped of their outer hydrogen and helium layers. As the core collapses into a black hole, jets of relativistic plasma are launched from the poles, punching through the outer layers of the star and blasting out into space. These are the beams you now witness. They travel nearly at the speed of light. Within them are exotic particles, tangled magnetic fields, and gamma rays so intense they can disrupt the bonds of atoms. And yet, from your safe vantage, they shimmer like ribbons of ghostlight. You watch the jets unravel the outer shell of the star, tearing apart what was once a stable fusion machine and flinging it into the abyss. The explosion will eventually settle into a supernova remnant, but the GRB is a moment apart, a flashpoint of terrifying beauty. No one on Earth sees it. It's too far. But somewhere, a telescope in low Earth orbit will catch it. A dot on a screen, a spike in data, a warning that somewhere in the vast dark, another Titan has fallen. And here's the scientific puzzle. Why do only some massive stars produce GRBs? Two stars of similar mass and composition may die entirely differently, one in silence, the other in a blaze of gamma light. Some researchers think rapid spin is the key. Others believe it's tied to low metallicity, meaning stars born with fewer heavy elements are more likely to produce the narrow, relativistic jets needed for a GRB. There's even debate about the role of magnetic fields in channeling the jets through the collapsing core. Scientists still argue whether gamma-ray bursts are more common in early galaxies, where low metallicity stars were more prevalent, or whether we've simply missed many nearby ones because the jets weren't aimed at us. It's the ultimate cosmic roulette. If you're in the path, you see everything. If you're just a fraction of a degree off, you see nothing at all. That's part of what makes them so mysterious. And there's more. Short-duration GRBs are an entirely different beast. They don't come from dying stars, but from merging neutron stars. Imagine two neutron stars locked in a death spiral. They orbit each other for millions of years, slowly losing energy through gravitational waves. Then, at last, they collide. The force of that collision doesn't just create a blast, it reshapes reality. It emits gravitational waves detectable by LIGO and Virgo. It sends gamma-ray bursts out into space, and in the fiery wreckage, it forges something rare and ancient. Gold, yes, gold, and platinum, and uranium, and other heavy elements. Most of the gold in the universe, including the atoms in your wedding ring or your grandmother's necklace, were likely born in these cataclysmic events. Not in a star, not in a supernova, but in the crash of two neutron stars. You close your eyes for a moment and let that sink in. Something so delicate, so cherished, so personal, born from a collision so violent it warped the structure of space-time. It's humbling. You glide now through the theoretical aftermath of such a merger. A cloud of expanding debris spirals outward, glowing in strange colors, what scientists call a kilonova. It's fainter than a supernova, but richer in mystery. Within its light are signatures of exotic nuclei, lanthanides, actinides, elements that form the deep threads of planetary crusts and technological marvels alike. And yet, this is all new. The first confirmed detection of a kilonova occurred only in 2017 when the event GW Sun 170817 was observed via both gravitational waves and light. For the first time, astronomers watched a neutron-star merger unfold across the electromagnetic spectrum and in space-time itself. That was only a few years ago. What else don't we know? There's still debate about what's left behind after such a merger. Is it a heavier neutron star, a black hole, a strange intermediate object, perhaps a quark star? Scientists are still collecting data, still piecing together models, still hunting the skies for more examples, and each new detection helps rewrite the rules of cosmic death. You think back to the beginning of your journey, your first glimpse of the dying star, the flash of its outer layers, the cold pulse of its neutron heart. Now look how far you've come. From Type 2 collapses to Type Ia detonations, from failed supernovae to black holes, from GRBs to kilonovae. Each is a unique stanza in a universal poem. Each has its own tone, its own tempo, its own truth. Some scream, some whisper, some vanish without a trace, but all are woven from the same threads of mass, gravity, fusion, and fate. And now, something stirs in the back of your cosmic mind, a quiet knowing. The violence of supernovae is not random, it is ritual, it is necessity. Without them, there would be no iron in your blood, no calcium in your bones, no planets to walk, no light to see, no tools to build telescopes with. Every piece of you was once flung from a dying star. Somewhere, billions of years ago, there was a supernova whose shockwave passed through a cold gas cloud. It compressed that cloud just enough for it to collapse. That collapse became a sun. That sun gave life to a planet, and on that planet, life awoke and stared at the stars. And now you are here, floating beside a gamma-ray burst in the quiet between explosions, feeling the deep, slow pulse of the universe unfolding. You breathe in and drift forward again. You drift now through the quiet after the storm, passing through cooled embers of ancient violence. Around you, the galaxy spins on, oblivious. Stars burn, dim, die, and are reborn across the spiral arms, each one playing its part in the cosmic symphony. You've traced the death throes of stars, seen them burn out in silence, collapse into darkness, explode into brightness that rewrites space-time. But tonight, you follow another path, a more delicate one. Not all supernovae are created equal, and not all of them end alone. You turn toward a different kind of story, one of companionship, of gravitational bonds that twist until they tear. You are heading toward binary systems, pairs of stars so close their fates are inextricably entangled. Many of these end in violence, and some in strange, slow unravelings. There it is. You approach a pair of white-hot stars circling each other in a tight, decaying orbit. From a distance, they look almost peaceful, like two fireflies chasing one another around a still pond. But as you drift closer, the tension becomes clear. These are white dwarfs, ancient stellar cores, burned-out relics left behind by sun-like stars. They're dense, dim, and old, and they're drawing closer every second, spiraling in, the space between them shrinking, not because of heat or magnetism, but because of something far subtler, gravitational waves. These ripples in space-time bleed energy away from the system, carrying momentum into the void. Slowly, quietly, the two stars lose height in their orbit. The dance tightens. Eventually, inevitably, they will merge. What happens next depends on their combined mass. If it remains under the Chandrasekhar limit, about 1.4 solar masses, they might form a single, more massive white dwarf. But if the mass exceeds that threshold, a catastrophe unfolds. You begin to see it now. The two dwarfs touch. Material flows from one to the other in a brief, furious transfer. Then, all at once, the mass crosses the limit. Boom. A Type Ia supernova, born not from theft, as in accretion from a main sequence companion, but from a merger. The two white dwarfs become one, and that one explodes. Completely. No remnant, just ash and light. This is one of the many proposed progenitor systems for Type Ia supernovae, and scientists still argue which is more common, the single degenerate model, a white dwarf stealing mass from a normal star, or the double degenerate model, two white dwarfs merging. So, observations seem to favour mergers, especially in older galaxies where massive stars have long since died. Others suggest both mechanisms contribute. The debate continues. You float among the debris, watching elements swirl and scatter. Iron, nickel, silicon, all the building blocks of worlds, of bones, of blood. These heavy elements will drift for millions of years before settling into some new cloud, some new world. But not all binary systems end in explosions. Some end in something stranger. You pivot gently through space and locate another system, farther away, quieter. Here, a neutron star orbits a more ordinary stellar companion. The neutron star is invisible in the optical, but in X-rays, it screams. You're now observing an X-ray binary, a system where a dense object, like a neutron star or black hole, feeds on the outer layers of its companion. The stolen matter forms a glowing disk around the neutron star, heating up to millions of degrees as it spirals inward. You pause above the disk. It's hypnotic, brilliant, whirling, unstable. The closer the gas gets to the neutron star, the faster it spins. Magnetic fields twist like ropes under tension. Periodically, chunks of matter fall inward, crashing onto the neutron star's surface and releasing bursts of energy. This process isn't just violent, it's transformative. Matter from the companion star is slowly lost, thinning its atmosphere. Eventually, it may shrink into a brown dwarf or be destroyed entirely. And the neutron star, it spins faster and faster as it accretes material. Over time, it may evolve into something remarkable, a millisecond pulsar, spinning hundreds of times per second. You've seen some already, but here you understand them better. Their spin is not a birthright, it's earned, gathered over millions of years through this cannibalistic dance. It's as though the star steals youth from its partner, becoming faster, harder, more precise. These recycled pulsars, as they're sometimes called, are among the most stable clocks in the universe. So stable, in fact, that we use them to study gravitational waves. Scientists build networks of millisecond pulsars scattered across the galaxy like pebbles on a pond. By watching tiny shifts in their timing, billionths of a second over years, they hope to detect the stretching and squeezing of space caused by passing gravitational waves. You float among them now, listening to their rhythm, steady, reliable, the heartbeat of a galaxy written in pulses of radio light. And just when you think the narrative is slowing, just when the death of stars seems almost manageable, something shifts again. You come upon a remnant unlike any other. It doesn't shine, it doesn't pulse, it devours. A black hole in a binary system, silently feeding on its companion star. Material swirls into an accretion disk, spiraling ever inward. Jets shoot out from the poles, thin, fast, nearly invisible to the naked eye. This is Cygnus X1, the first black hole ever confirmed. Discovered in 1964 through its X-ray emissions, Cygnus X1 was the subject of fierce debate. Could it be a neutron star, an exotic object? But measurements eventually confirmed its mass was too great. It had to be a black hole. It was a landmark discovery. And yet it is just one of many. You pass others, V404, Cygni, LMC, X3, each a point of darkness in a binary dance, pulling matter in with inexorable force. Some are quiet, some flare with sudden outbursts as matter piles up, then collapses inward in great waves. The physics here is extreme. As matter falls toward the black hole, it reaches a fraction of the speed of light. The energy released lights up the disk, creating flickering patterns that we can see from Earth, each flicker telling us something about the geometry of space-time near the event horizon. Scientists still debate how much of this accreted material actually falls in and how much is blown away in winds and jets. Some models suggest as much as 90% of the matter never reaches the black hole, but is instead flung outward. What a paradox. The most powerful objects in the universe are also the most wasteful. You drift outward again, watching a final set of binaries. These are quiet now. The light is fading. The systems are old. One has a white dwarf and a brown dwarf, their orbits slowly decaying. Another is a millisecond pulsar with no companion, its partner long since evaporated. A third is a neutron star drifting alone, kicked out of its binary by a supernova that destroyed its twin. They are all remnants, ghosts, echoes of something more, and they remind you of something profound. In the end, death is rarely solitary. Stars live in families, clusters, binaries, triplets. Their deaths are intertwined, entangled, and often prolonged by these connections. A supernova is not always the end. Sometimes it is the beginning of a more complex relationship, a gravitational bond that refuses to die. And so you float on. Watching these slow dances, these gentle deaths, these strange survivals, not with fear, but with awe, because here, in the final embers of stars, you see something beautiful. You see how the universe remembers, not with words, but with light. You wander now through a quieter part of the cosmos, not because it is any less dramatic, far from it, but because this region has aged. The supernovae have all gone off. The neutron stars have spun themselves to stillness. The black holes feed only occasionally now, content with the dim husks of gas clouds drifting nearby. What's left are the echoes, soft, sprawling, the long aftershocks of ancient violence. You've come to the supernova remnants, the ghostly veils left behind after stellar explosions. Here you do not witness the moment of death, you walk through the memory of it. The first thing you notice is color, not the fiery burst of an explosion, but a more delicate palette. Faded blues, pastel greens, the crimson fingers of ionized hydrogen. It's as though the light itself has grown reflective, tired, but still dancing. While you're passing through the Veil Nebula, a remnant of a supernova that exploded some 10,000 to 20,000 years ago. Located in the constellation Cygnus, it's enormous, spanning more than 100 light-years across, yet its filaments are thin as smoke, rippling with the turbulence of expanding gas. This nebula is so vast and diffuse that from within you barely notice its edges. You glide along waves of oxygen that glow turquoise in the ultraviolet. Tendrils of sulfur thread through the clouds like veins. Hydrogen gas pulses faintly in reds, shaped by magnetic fields still trembling from the explosion. This is not debris, it is structure, the fingerprint of a dying star. Each remnant you visit tells a different story. Some are spherical, neat, almost gentle. Others are jagged, lopsided, as if the star died with unfinished business. The shape of a supernova remnant is dictated by dozens of factors: the star's rotation, its composition, the local environment, whether it had a companion star, even the direction of its final convulsions. Some remnants are almost impossible to recognize. Others have names that feel like ancient poetry: the Crab Nebula, the Cygnus Loop, RCW 86. Each one a page in a cosmic journal, each one telling you in its own silent language what kind of death birthed it. You pass into the Crab Nebula, glowing with eerie brilliance. This one is young by cosmic standards, just under 1,000 years old. It was observed in 1054 CE by Chinese astronomers who recorded a guest star in the sky bright enough to be visible in daylight for weeks. Some even believe that Native American petroglyphs may record its sudden appearance. And at the center of the crab is a neutron star, a pulsar spinning 30 times per second. This, you realize, is something special. The crab pulsar isn't just a survivor, it's an engine. Its spin powers the entire nebula. Electrons scream away for it on its poles at near light speeds, coiling into spirals of synchrotron radiation that light up the surrounding gas. You feel the pulse pass through you, steady and cold. It is a heartbeat echoing from the grave. You circle the pulsar slowly, watching its beams strobe across the nebula. It is a lighthouse for a lost world, and it reminds you, not all supernova remnants are inert. Some remain alive in their own way, animated by the corpses they cradle. Scientists still argue whether all supernovae leave behind such remnants. Some seem to disappear entirely, with no visible nebula, no neutron star, nothing at all. Are we missing them? Or are there types of stellar deaths so complete, so total, they leave no visible mark? The debate continues. You drift away from the crab and find another remnant, RCW 86. It lies in the southern sky, in the constellation Circinus. This remnant is special because it may correspond to the first recorded supernova in human history, a bright event noted by Chinese astronomers in 185 CE. For centuries, that record was a mystery. Only in recent decades did X-ray and infrared observations confirm that RCW86 is a likely match. You peer into its heart. Unlike the structured chaos of the crab, RCW86 is sprawling and complex, suggesting a Type Ia origin, a white dwarf obliterated in a thermonuclear runaway. There is no neutron star here, just an expanding cloud still glowing after nearly 2,000 years. You wonder about the ancient skywatchers who first saw it. What did they think? A divine omen? A tear in the heavens? They didn't know about fusion or degenerate matter, about gravitational collapse or nuclear chains. And yet their eyes caught the same light you now trace. The same cosmic breath. You pass now through W49b, a strange and lopsided remnant that may have been caused by a jet-driven supernova. A rare and exotic explosion where material was flung out not evenly but in narrow jets, perhaps akin to a gamma-ray burst. Inside it may lie a black hole instead of a neutron star. If true, W49b would be one of the feeds. With supernova remnants suspected of having birthed a black hole directly. The evidence? A peculiar morphology, more cigar than sphere, and an absence of a central pulsar. But we can't be sure. Scientists still argue whether the shape is intrinsic or the result of an uneven environment. Dust, after all, plays tricks with symmetry, and black holes, being what they are, remain silent. As you explore the remnants of ancient stellar death, you begin to notice something unexpected: life. Not conscious life, not organisms or thought, but formation. In the trailing edges of these clouds, where shock waves have passed and cooled, new structures are forming. Tiny knots of gas, denser than their surroundings. Pre-stellar cores. You pass a region where a supernova's blast compressed a nearby molecular cloud, causing part of it to collapse. This is called triggered star formation, where one star's death jump-starts the birth of another. You glide through these rippling clouds, watching dark filaments tighten into threads, then beads, then the first whispers of gravity-bound systems. These are the cradles of tomorrow's stars. Some will burn hot and fast, others will smolder quietly for trillions of years. Around them, disks will form, planets, moons, dust and ice and rock. It's happening all the time. Supernovae do not simply destroy, they seed, they press the gas of galaxies into shape, they stir the ingredients of complexity, and in their debris are the elements essential for rocky planets, for magnetic cores, for water, for DNA. You too are built from the dust of long-dead stars. Your bones carry calcium made in stellar cores. Your hemoglobin binds iron born in supernovae. The iodine in your thyroid, the potassium in your neurons, all born in fire billions of years before your birth. And yet here you are. Observing the cycle from within and without, a child of stardust, dreaming of the stars. You linger a moment longer inside the shell of one final remnant. It is large and quiet, its central engine long since cooled. Dust floats through it like snowfall. Light glimmers faintly on its farthest edge. You press your weightless palm against the invisible wall and listen. It's still humming, not with sound, but with memory, with structure, with the soft, expanding breath of something that once lived and died and still, in a way, lives on. This, you think, is not a graveyard. It's a nursery in reverse, a place where endings make room for beginnings. And now the stars call again, new stories, new collapses, new flares in the deep. Your journey continues. You rise gently from the tapestry of supernova remnants and float higher, lifting out of the debris fields like mist off a forest floor. The dust thins, the stars brighten, and silence settles once again around you. But within that silence, you feel it. Pressure, momentum, potential. The story of supernovae is not finished with death. No. There is one more destiny still unwritten, one more path whispered by gravity and carved into the mathematics of the cosmos. You are about to enter the realm of black holes. but not the tiny ones, not the stellar mass husks left behind by collapsed stars. You've already passed them. Cygnus X1, V404 Cygni, those singularities that weigh 10, maybe 20 times the mass of the Sun. Here, now, you look towards something far larger, monsters. In the center of nearly every large galaxy lies a supermassive black hole, with masses ranging from millions to billions of solar masses. And while these behemoths are not born from ordinary supernovae, their roots are tied to the deaths of stars, perhaps many stars, collapsing and merging over and over in the earliest epochs of the universe. You cross into the galactic center, your path narrowing into a swirl of magnetic chaos. This is the heart of the Milky Way, a dense, crowded region brimming with old stars and strange X-ray signals. And at its core sits Sagittarius A, our galaxy's central black hole. It's quiet now, dormant, not currently feeding, but you can sense it. You drift closer, moving through clouds of dust and fast-moving stars, their orbits twisted into ellipses by the black hole's gravity. The closer you get, the more distorted things become. Light curves, time stretches. You're entering a zone where the rules you know begin to fray. Sagittarius A has a mass of about 4 million suns, compressed into a space smaller than your solar system, and despite its size, it emits almost no light. In fact, the black hole itself emits none. What we see, what you feel here, is the glow of accretion. Gas heated to millions of degrees, electrons spiraling in magnetic fields, flickers of radio and X-ray pulses tracing the threshold of oblivion. Here's a peculiar thing. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, not Sagittarius A, but its cousin in the galaxy M87. Still, that image changed everything. For the first time, humanity saw the silhouette of the event horizon, saw light bent and trapped around a singularity. In 2022, the EHT followed up with an image of Sagittarius A itself, blurred, flickering, elusive. Because our black hole is smaller and faster spinning than M87's, its appearance shifts constantly, like a flame caught in wind. Scientists still debate whether the light pattern reveals anything about spin, charge, or inclination. They argue too about how such black holes formed. One leading theory suggests that direct collapse black holes formed in the early universe, massive clouds of pristine hydrogen collapsing straight into singularities without ever igniting as stars. Others believe that populations of massive stars, born in primordial galaxies, exploded as hypernovae, leaving behind seed black holes that merged and grew. The data is still sparse, the models still fragile, but your presence here. E suspended before Sagittarius helps crystallize a simple truth. Stars die. Sometimes they die into something small, a white dwarf, a neutron star, and sometimes they die into forever. As you circle the black hole, you observe nearby stars zipping by at incredible speeds. One, known as S2, completes an orbit in just over 16 years. It reaches speeds over 7,600 km/s as it swings around the black hole. Observing this star's motion allowed astronomers to confirm Einstein's predictions about general relativity, how time dilates, how light redshifts in extreme gravity. You pause and think. A single supernova, somewhere in the ancient center of the Milky Way, might have flung that star into its present orbit. Stellar deaths shaping galactic dynamics like cosmic billiards played over millennia. But black holes aren't just endings. You look outward now to the great web of galaxies and realize, without black holes, galaxies themselves might not exist in the forms we know. The feedback they provide, jets, winds, radiation, regulate star formation. Galaxies with overactive central black holes tend to quench, halting new stars from forming. Others, calmer ones like the Milky Way, nurture stars for billions of years. It's a balancing act. Some scientists even propose that the relationship between black hole mass and the surrounding galaxy's bulge is not just correlation, but causation. that somehow a single dying star collapsing into a black hole and feeding over time can shape the very architecture of the galaxy around it. From death, order. From collapse, design. There's another theory that chills you with its elegance and dread, the Big Bounce. A speculative idea, fringe but poetic. It suggests that the universe may not have begun with the singularity in the Big Bang, but emerged from the collapse of a previous universe through something like a black hole. In this view, black holes are more than stellar graves. They are seeds of new universes. Scientists still argue over the possibility, whether quantum gravity permits it, whether the inside of a black hole cysts and ever birth anything at all. But you consider it gently. A star dies. It explodes or collapses, and somewhere inside that death, inside that singularity, there could be a beginning. Maybe the stars that made you were born inside a black hole long ago. Maybe every supernova is a doorway. And maybe, just maybe, some stars die not in our universe, but into another. You breathe that possibility in, let it fill the silence. Around you, the galaxy turns. You see its arms from this vantage point, curling like smoke around the black heart you hover beside. The stars flicker like dreams, scattered across time. And all of it, the stars, the nebulae, the remnants, the planets, everything is shaped by the violent deaths of ancient suns. Without supernovae, there would be no iron, no earth, no thinking, dreaming being to look up at the night sky and ask, where did this all come from? You came from this, from a star that lived, burned, died, exploded, and left behind the raw ingredients for life. That star is long gone, but its death is you. You glide now beyond the galactic core, leaving behind the brooding pull of Sagittarius A, its influence tugging at the fabric of space-time like a stone sunk deep in water. The stars begin to thin, the gas grows colder. You're headed for the outer edges now, those quiet galactic hinterlands where old stars coast on long elliptical orbits and time seems to forget itself. It's here, amid this stillness, that you sense something profound. The story of stellar death is not complete without understanding the long tail of its consequences, the cosmic recycling that happens over millions, even billions of years. Because while the death of a star may take seconds, its aftermath can reshape galaxies for epochs. You pass a stellar stream, shards of a long-gone star cluster torn apart by tidal forces. It's barely visible, a river of motion through deep space. In its faint flow are elements forged in supernovae, calcium, cobalt, zinc. These atoms will wander for ages, drifting into molecular clouds, waiting to become parts of something new. You approach one such cloud, a dense, frigid mass of hydrogen laced with dust. It's darker than the void around it, opaque even to starlight. But inside, gravity has begun to work. Tiny pockets are collapsing, heat is building, protostars are kindling to life. You remember this place, not this exact cloud, but this process, because it's where all stars begin, even the ones fated to die in supernovae. It's strange, isn't it? That death paves the road for birth, that the very force that tears apart a dying star, the dispersal of its atoms, feeds the next generation. And yet this cycle is not infinite. You glide past stars that will never die in fire. Red dwarfs, tiny and efficient, will live for trillions of years, burning their hydrogen with gentle thrift. They won't go supernova. They'll fade quietly, turning into black dwarfs, hypothetical objects since the universe isn't old enough for one to exist yet. But eventually, they too will grow cold, hard, dead. Even white dwarfs, given unimaginable spans of time, will radiate their last warmth. Neutron stars will slow, their magnetic fields decaying. Black holes will evaporate through Hawking radiation, whispering away their mass over quadrillions of years. And in the very, very far future, so far that your human sense of time no longer applies, the universe itself may reach heat death, a state where no energy remains to do work, where everything is cold, spread thin, and still. It's a theory, one among many, Scientists still argue whether dark energy will accelerate the universe into oblivion, or whether something unforeseen will stop it. A new field, a reversal, a bounce. But for now, for this moment, the cycle continues. You turn back to look at the clouds again. Inside them, some of those new stars will be massive, hot, destined to burn bright and die quickly, perhaps within a few million years. One of them will be like SN1. 987A, the first supernova visible to the naked eye in nearly 400 years. You recall how, in 1987, astronomers on Earth noticed a bright light in the Large Magellanic Cloud, a blue supergiant detonating its layers outward in an asymmetric blast. It gave scientists an unprecedented look at the neutrinos, ghostly particles streaming from the collapsing core. Those neutrinos arrived at detectors hours before the light did, racing ahead of the explosion itself. It confirmed that a core collapse had occurred and gave us a glimpse into the very mechanism of a star's final breath. But it also raised questions. Why was the progenitor star a blue supergiant when red supergiants were thought to be more common supernova precursors? Was it an oddball case, or have our models missed something? Even now, decades later, astronomers still debate the physics of SN 1987A, its ring structures, its asymmetries, the mass of its remnant. It is a puzzle, glowing faintly in the southern sky. You drift past its echo, a wave of matter expanding at thousands of kilometers per second. You wonder what alien civilizations might see when it reaches their telescopes, whether they too will marvel at the symmetry and chaos entwined in a star's final act. As you fly onward, a shape resolves in the distance, not a star, not a remnant, but a galaxy. Spiral arms, rich with dust lanes and blue-white star clusters, coil around a bright central bulge. This one is unfamiliar, not your Milky Way, a neighbor, perhaps, a snapshot of a different place, a different time. You scan its outskirts, tracing the gradients of star populations. The outer edges are filled with younger, hotter stars. The center holds red giants, and somewhere inside, likely another supermassive black hole. Supernovae are going off there too, right now, silent from your vantage but loud in their effects. And as you peer deeper, you notice so mething beautiful. Galaxies are not isolated. You see faint bridges of gas stretching between this galaxy and another, tidal tails, debris from past interactions. Stellar streams, collisions, and in those crossings triggered waves of star formation, chain reactions, supernovae lighting up new regions like brush fires on a cosmic scale. The universe is not static, it is a living thing, a breathing, moving, ever-evolving web. Stars die, galaxies merge, elements scatter, and from all of it, new light is born. Somewhere in that distant spiral, a planet forms. Water condenses, chemistry stirs, lightning strikes, molecules dance, and in the faint warmth of a young star, something begins to think, to wonder, to gaze up and ask questions, to build telescopes, to dream. You realize softly now that supernovae are not simply about death. They are about connection, the way one event ripples through time, shaping the birth of worlds, the formation of matter, even the thoughts in your own head. You have always been part of this story, not outside it, not merely an observer. You are composed of consequences. You are made from stellar decisions, from pressure and fusion and collapse. And tonight, as you drift through galaxies, you feel not separate from them, but threaded into them, a strand in the cosmic fabric. A witness, a memory, and a continuation. And now, the journey nears its end. You drift quietly beyond the tangle of galaxies, out where the cosmic web stretches thin, past the filaments of clustered matter, past the voids where almost nothing stirs. This is the frontier, the cold edge, and even here the echoes of supernovae linger like forgotten lullabies. There is silence here, yes. But it's the kind of silence that comes after a story has been told, a reflective hush, rich with memory. Above you? No. Around you, stars still die. Right now, at this very moment, somewhere in the observable universe, another massive star reaches its tipping point. The fusion in its core has faltered, gravity has gained the upper hand, and as the layers collapse inward, something ancient unfolds once more. It begins as neutrinos flooding outward in a ghostly exhale, then a ripple of energy, then light, another supernova. You'll never see it, not directly. It may be 10 billion light years away. Its glow will take eons to reach where you are, but its consequences are instant. The universe grows just a little more enriched, just a little more complex. Another whisper of iron joins the void. Another pulse of gamma rays hums through the fabric of space-time. And so the story continues, even as you pause to rest. You've seen the mechanics: gravitational collapse, electron degeneracy, runaway fusion. You've witnessed the types: type Ia, type 2, hypernovae, kilonovae, failed supernovae. You've watched the remnants evolve: white dwarfs, neutron stars, pulsars, black holes. You've traversed the sites of ancient destruction and future creation. But now comes a softer truth. You are the product of all of it. The calcium in your teeth, forged in a supernova. The potassium in your cells, scattered from a stellar core. The gold you might wear on your finger. The oxygen you breathe. The silicon in the device that delivered you this very story. Every one of them was born in fire. Somewhere, long ago, a star gave its life so that atoms could assemble, drift, combine, and one day think. And here you are, billions of years later, still burning in your own quiet way, a tiny sun inside a skull, processing light into memory, processing wonder into understanding. You float now, not as a traveler, but as something timeless. The line between observer and participant has blurred, because death, you now see, is not an end but a redistribution. And supernovae? They are the universe's greatest act of generosity. They take one thing, one single isolated star, and explode it into everything, from one, many, from destruction, design, from chaos, for... Even now, as the galaxies wheel slowly in the distance, and cold photons from the oldest stars streak past your cheeks, the universe continues to evolve in this strange, poetic way. A dance of thermodynamics and randomness, entropy and structure, and always, always at the center of it, the deaths of stars. You pass one more remnant, it's barely visible. A thin veil of gas, centuries old. The star that made it is long gone. Nothing pulses here anymore. Nothing radiates. And yet, in that emptiness, something blooms. A faint reflection, not of light, but of meaning. You press your hand, real or imagined, against the edge of that gas. You close your eyes. You feel the weight of eons and the flicker of seconds. You hear the heartbeat of gravity, slow and inexorable. And you understand, fully now, stars must die so that the cosmos can live, so that elements can blend, so that planets can rise, so that something with eyes and ears and dreams can look back at them and whisper, "I remember." You are that whisper. You are that memory. And now, let us fade into quiet. Let us soften the edges. Let us wind down. The universe begins to dim around you now, like the last flicker of a candle in a dark room. The stars grow more distant, the explosions quieter, the fabric of space folding itself gently back into silence. You are no longer flying, no longer tracing shockwaves or watching gravity tear the sky apart. You are resting. The elements that built you, iron, carbon, oxygen, return to a gentle stillness. The breath of supernovae cools into memory. Their roaring force fades into background hums and soft echoes. You feel your thoughts slow, like dust settling onto the floor of a nebula. You are made of star stuff, yes, but even star stuff needs sleep. Let yourself drift now. The galaxies will continue their spiral. The pulsars will keep ticking. The black holes will wait patiently. The light will still travel endlessly. But for now, none of that is your concern. You've journeyed across millions of light years, through fire and time and collapse and rebirth. You've seen suns die and stars form. You've touched the bones of the cosmos and heard its breath. And now, the only thing left to do is to rest. Close your eyes. Let the nebulae wrap you in their gauze. Let the starlight lull you into stillness. You've earned it. Good night, fellow traveler, until the next journey.